Our first question is, where are the electrons in organic structure? The good news is that there's only three possibilities, right? The only places that electrons can exist in organic structure are in sigma bonds, pi bonds, or in lone pairs. And so just a quick reminder, right? Sigma bonds are connecting bonds. These are bonds that connect atoms to other atoms, right? The simplest example is a single bond between two atoms. Pi bonds are the multiple bonds. So anytime you get above a single bond, right, when you make a double bond, that second bond that's connected between those two atoms is a pi bond, multiple bonds. So these are double or triple bonds. And lone pairs are, of course, non-bonding electrons. And so these are electrons that are not involved in any kind of bonding. Exist there. So if we look at, well, the example that we used before was Adderall for organic structure. Adderall has actually examples of all three types, right? We have a sigma bond. All of these carbon-carbon bonds, right, are sigma bonds. Here, these single bonds that are here, the carbon-nitrogen single bond that's there. We have lone pairs that are here, and we have pi bonds in the six-membered ring here as well. So these are all pi bonds. Here, and here. And so a simple structure like this even still contains all three of those locations. So a couple of things to point out. When we have a single bond or a double bond, right? When we have a double bond, for example, a carbon-carbon double bond, a carbon-carbon double bond consists of both a sigma bond and a pi bond. When we have a carbon-carbon triple bond, or any kind of triple bond, right? We have the connecting bond, and this is a sigma bond. But then we also have the other two bonds that connect these two carbons together. Each of those is a pi bond. And so a triple bond consists of a sigma bond and two pi bonds. Okay. So a single bond is only a sigma bond, a double bond is a sigma and a pi bond, and a triple bond is a sigma bond and two pi bonds. So whenever we draw these structures, we're looking at where are the sigma bonds, where are the pi bonds, where are the lone pairs, right? So we're going to start with carbon and hydrogen because those are kind of the simplest ones. We're going to use the octet rule to kind of figure out what types of bonds and how many we can form, and then we're going to talk about the different types of bonds that we can make. The good news about carbon and hydrogen is because of the octet rule and the number of valence electrons, carbon has 4 valence electrons, hydrogen has 1, and we figure that out just from the periodic table. Because of the way this works, every neutral carbon atom will have 4 bonds and no lone pairs. Right? And the reason that this is true is because of the application of the octet rule, right? In order for carbon to have a full octet, it needs to use its 4 valence electrons and surround itself with 8 total electrons. And that means that it has to share each of its valence electrons in a bond in order to end up with 8 total electrons. So it has to make 4 bonds with its 4 valence electrons. Those 4 bonds have 2 electrons in them each. That makes a full octet. But in order to make those 4 bonds, it uses all of its valence electrons, so there are no electrons left over to make lone pairs, and so every neutral carbon will always have 4 bonds and no lone pairs. This is an incredibly important statement. Neutral carbons have 4 bonds and no lone pairs. This is always true. Right? If you have a carbon that doesn't satisfy one of these criteria, then the others are no longer true. Right? If you have a carbon that has a lone pair, then you can't have 4 bonds and it can't be neutral. If you have a carbon that is not neutral, then you either have a different number of bonds or you have a lone pair that's present, right? If you don't have four bonds, you either don't have a neutral carbon or you're going to have some kind of lone pair in it, right? And so all three of these things play off of each other. They're all true. And so remembering always that any neutral carbon has four bonds and no lone pairs is incredibly important. Hydrogen is a little bit simpler. Hydrogen only has one valence electron. Hydrogen also has no lone pairs, neutral hydrogen, no lone pairs, but can only have one bond, right? Forms one bond. And that bond is, of course, always a sigma bond because the first bond that you form, the connecting bond, is always a sigma bond. So hydrogen is sigma bonds only, no lone pairs, a very straightforward atom for us to deal with. Carbon is a little bit more complex because carbon can have kind of various different ways of satisfying its octet. And the way that we look at this is we look at the types of bonds that surround it, right? Once again, we have sigma bonds and pi bonds as our option. And so we can look at three different types of carbon. Right? The first type is an sp3 carbon. So this is hybridization. You've probably seen this in general chemistry, right? We're going to take each of the valence orbitals of carbon, one s orbital, one 2s orbital, and three 2p orbitals. We're going to mix them together, create four equivalent bonding orbitals, and that means that that carbon can now be connected to four other atoms. I'm going to use hydrogen here. They do not have to be hydrogens, right? It could be connected to any other element, but in this case, hydrogen is kind of the simplest, right? So this sp3 carbon has four sigma bonds and no pi bonds. sp3 carbons are usually pretty easy to spot. They have no lone pairs because neutral carbon has no lone pairs, and they tend to have, and they also have no pi bonds connecting them to anything else. So any carbon that doesn't have any pi bonds coming into it will mostly be sp3, right? sp2 carbons are the next flavor. sp2 carbons are carbons that have one pi bond associated with them. And so we have, in this case, have two sp2 carbons connected to each other. This carbon is sp2, this carbon is sp2. And we can see the types of bonds that we have here. We have a sigma bond, pi bond, and then all the CH bonds are sigma bonds. And so if we look at which types of bonds are surrounding each carbon has four bonds surrounding it. It has three sigma bonds and one pi bond. And so each of the carbons is sp2 hybridized, right? If we count just the four bonds connected to the carbon on the left, you get three sigma and one pi. If you count the four bonds connected to the carbon on the right, you get similarly three sigma and one pi. The last flavor of carbon is an sp hybridized carbon. This is a carbon with a triple bond. We've already talked about triple bonds, so you kind of know what to expect here. This is two sigma bonds, right? That carbon has a sigma bond to the hydrogen going off to the left, and also a sigma bond to the carbon on its right. But the triple bond also contains two pi bonds, and so we have two sigma and two pi. And so depending on the number of sigma bonds and the number of pi bonds, pi and sigma, right? Depending on the number of sigma bonds and pi bonds, we have carbons that have different hybridization. Right? Notice that the hybridization is the atom itself, right? The carbon atom is sp3 hybridized, or sp2 hybridized, or sp hybridized. Right, we refer to each atom as having its own hybridization. Each of these hybridizations has a bond angle associated with it as well. We get to that from valence shell electron repulsion theory, another holdover from general chemistry, right? But mostly what we want to say is each of these bonds moves as far apart from each other as they can be. And so if we look at an sp3 carbon, these bond angles are all 109.5 degrees, right? This is three-dimensional, and so some of these bonds will be coming out of the plane of the screen, and some of them will be going back into, oh, stop, there we go. Some of them will be going back into the plane of the screen, but the bond angle at each point here is 109.5 degrees, and that comes from geometry, right? So sp3 carbons have a 109.5 degree bond angle. That's generally always true. sp2 carbons, because they have to make space for the pi bond, are all flat, and so there's no three-dimensional structure, and the bond angle here is 120 degrees. Right? Every bond angle is the same. Right? So 120 degree bond angle for every sp2 carbon. Now the sp carbons is where it gets a little bit harder to visualize, but in this case the bond angle now is 180 degrees, right? All these electrons are moving as far apart from each other as they can be. We have the triple bond being 180 degrees from the single bond. And so every sp carbon will have a bond angle of 180 degrees. And so this allows us to kind of see the shape of these molecules, which will become important when we get to reactivity.